Okay, so let me introduce the first speaker of today. This is Elba Garcia-Failde from the University of Paris, and she's going to talk about cohomological field theories and topological recursion. Please.
Thank you, Corina, for the introduction. Well, first of all, thanks a lot to the speakers, to the organizers, and also to the speakers. It was a great conference, but thanks to the organizers for giving me the opportunity to speak and also for organizing this nice event. So yeah, as Corina said, I will talk about cohomological field theories and topological recursion a bit in general, and then we will go to a particular example. So let me go directly to the outline of my talk. So as I was saying here, I will be talking about this procedure called topological recursion in general. Then I will tell you about Witten's conjecture, Kontsevich theorem. You probably heard about this, but it's kind of the beginning of this work. And then I will tell you the relation to cohomological field theories in a quite general setting. So this should be kind of half of my talk. I will try to be slow here. And then here I have a lot of material, but I will skip a lot of details. But it's I think it's nice for you to see an example of an extension of this general framework. So we will be talking about Witten's R-spin class. Sorry, there are some little noises. Okay, so topological recursion is a procedure that was invented around 2004 in the context of large size matrix models. So large size expansions of matrix models. And then it was extended to a universal procedure that doesn't really need a matrix model anymore around 2007 by Enard and Anton. So at the beginning, there was also Chekhov, then the generalization was done by Enard and Anton. So in general, the goal of topological recursion, and this is a very vague goal, but it's to give you an idea of what it means in general, is to count in some sense that one needs to make precise in every case, surfaces of genus G with n boundaries. So we say that surfaces of genus G with n boundaries have topology Gn. I will be talking about this topology Gn all the time. But you saw in many talks during the week things with genus G and n boundaries or n mark points. So, okay, in general, the procedure takes some initial data that is called spectral curve that consists of a Riemann surface, then a ramified covering of this of CP1 by this Riemann surface, so a coordinate x. There is also another coordinate y, and then this x and y form for you a one form that has to do usually with the topology of disks, so 0, 1. And we also need a two form or a 1, 1 form that has to do with the topology of cylinders. Then by recursion on the absolute value of the Euler characteristic of a surface of genus G within n boundaries, so 2G minus 2 plus n, so it's a recursion on this quantity, we build some differential forms that live on this Riemann surface. So the procedure is done as is more or less depicted in this picture. So in this picture, you can find more or less all the details. I will not be giving all the details, but let's try to explain a bit how this works. So first of all, we need X to have finitely many simple ramification points. So ramification points, if you want to simplify a bit, is just zeros of dx. So you take the zeros of dx. You also impose that y is holomorphic around these zeros of dx, and dy is not zero. So this tells us that locally this covering looks like a square root. So it's not a singular point. This tells us that we have always an involution, a local involution around every ramification point. So since it looks like a square root, so it's a square root, it's important because it's simple ramification points. This is what we are allowing for the most classical topological recursion. You can also lift this condition, but it takes then a more complicated formula. So let's stick to this for the moment. So as I was saying, you have a local involution that we call sigma around every ramification point. So these 2 points, z and sigma z, they project to the same point by the ramified covering. So okay, we need this local involution about every ramification point. Then topological recursion, we said that it produces these omega GNs that are meromorphic forms. Then you can represent them. This is not something that that you should take as a definition at all. This is just a graphical representation for you to remember the formula. So these omega GNs, we can represent them with a surface of genus G with n marked points, as you see here. And the point of topological recursion is that you can build this information, whatever it is, we will see some examples, from simpler topologies. And by simpler topologies, I just mean that 2G minus 2 plus n in the right-hand side is smaller. You can check this. So all the terms of this sum. So first of all, the sum is overall ramification points of X. Then the computation is done via residues on the Riemann surface around these ramification points. And as you can see, to build the quantities inside the residue, we need this local involution around every ramification point, sigma A. Then there is a certain recursion kernel that I'm not giving the details at all about, but you can represent with these trivalent vertices or also with a pair of pens. You can see this as removing a pair of pens from this other surface that has a smaller minus Euler characteristic. And then here you have actually all the terms that you get if you remove a pair of pens from a surface of this topology. So in here you have the term in which when you remove the pair of pens, you get something connected. So you get something of topology G minus 1 n plus 1. And then you need to use this Z sigma A to evaluate it. And here you get all the possibilities of getting something disconnected when you remove a pair of pens from your surface. And I say here no 0, 1. This just means that we don't want to have any disk topology here, because otherwise I would be cheating and this would not be a recursion, because this would have the same topology as this one, the other one. So we discard this, and then this is really a recursion. So yeah, main observations. As I said, the terms are in correspondence with the ways of cutting a pair of pens. Maybe this I didn't stress, that the pair of pens sits on the first boundary of the surface. So this is the first curious thing, that this really seems non-symmetric at all, because the first boundary plays a very special role. But you can actually prove that the omega GNs that we are always interested in, and for sure the ones that comes from classical topological recursion, are going to be symmetric on all the variables. And well, we also know their pole structure. They only have poles at ramification points. Then we have a lot of interesting and powerful properties if we manage to prove that a certain problem satisfies topological recursion. So this is why we care, no? Because usually it's not easy to prove that your problem satisfies topological recursion. But if you manage, you gain for free, because there is this universal theory that is developed. You gain a lot of interesting and powerful properties. So one that is very powerful, I'm not explaining the details, but if you have a family of spectral curves, so imagine that you have a parameter that varies, then you know how the output varies along this family. This is very useful for many problems. And then the very, very nice feature of topological recursion is that the same formula works for many, many different problems with different flavors. So it's that's why we say it's a universal procedure. So here I give some examples in case this rings a bell for you. In the next slide, I will give you a bit more details of examples that are related to previous talks. So yeah, they count. So for example, Hurwitz covers are governed by topological recursion. These are just ramified coverings of the sphere. Then also certain graphs embedded on surfaces, Gromov-Witten invariants, volumes of moduli spaces, statistical physics models, not invariants. So okay, here this slide looks a bit ugly, but I thought maybe it was nice to give a list of connections or vague connections to other talks during the week. So yeah, the first one is that really Chern-Simons theory on S3 is governed by topological recursion. So okay, this is an bit of a toy model because you need to take the unknown and the group should be UN, I think, and then there are some generalizations, but it's not proved in general. But okay, in the first day, there were many talks about Chern-Simons theory. So this is definitely related to topological recursion. And the way that this was realized actually was through Gopakuman-Oguri-Baffa correspondence that gives an A model picture. So it gives a correspondence between Chern-Simons theory and Gromov-Witten theory of the resolved conifold. Okay, this you don't need to, if you don't know what it means, it doesn't matter. But the point is that this we know satisfies topological recursion. So topological recursion also allows us to find it helps us to establish these correspondences better, because you can prove sometimes that both sides satisfy topological recursion for the same spectral curves. So you have the correspondence and these type of things. So in this case, the topological recursion can be seen as a kind of B model. And we know that it should be applied to a spectral curve that is called like this. Okay, it's a mirror curve. And this might be regarded as a simplified setting for gauge string dualities, such as ADS-CFT correspondence that we saw a lot in the second day of the conference. And here you can find a very nice summary of this correspondence in the setting of topological recursion, in case you're interested. So yeah, actually this corresponds to, the fact that topological recursion governs Gromov-Witten theory was proved in a quite nice setting. So it was first conjectured by Bouchard, Clem, Marino, Pasquetti, and this was called the remodeling the B model conjecture. So, and then was proved later by Fang Liu Zhong in 2016. So if you apply topological recursion to the mirror curve of a toric Calabi-Yau threefold, it computes the open Gromov-Witten theory. Okay, and this is how you give the relation to the other problem. Yeah, then many statistical physics models are also related to topological recursion. You can consider them on random maps like Ising model, Potts model, Owen-Loop model. Okay. Then there is also this nice paper that goes from modular functors to cohomological field theories, and then it also shows that they are governed by topological recursion. Then it's a very important feature of topological recursion that it's related to integrability. It actually reconstructs formal WKB expansions, and it's related also in many cases to isomonotomic systems that we also saw in some talks. And here you have some important topics some important papers on these topics, but there are many more actually. Yes, and then I said that this reconstructs formal WKB expansions, but actually nowadays it's a very hot topic, the development of topological recursion in the non-perturbative world. So far it was a very successful theory for perturbative computations. And now there is a lot of work in progress to extend the framework of topological recursion to the non-perturbative world using this resurgence theory that we saw in some talk on Tuesday, I guess. Yes, and using this, we can also apply some analysis and remove the word formal from here, but this is really work in progress. And here I just give an example of a non-perturbative computation that is very nice, but it's actually a very conjectural thing. So there are many conjectures about the relations between topological recursion and knot invariance. And in this case, in the case of a hyperbolic knot, if you take the colored Jones polynomial, okay, you don't need to know the definition, but if you know it, then it's in the regime of this n going to infinity, which is the regime of the so-called volume conjecture. In this case, this was shown to be governed by topological recursion applied to the spectral curve given by the A polynomial of the knot. Sorry, I said it was shown. This is not true. This is just a check, a very highly non-trivial check, because it's up to many orders, but only for the figure 8 knot. And this is a conjecture in general, and it would help a lot with this volume conjecture, but it's very difficult because many people tried and it's hard. Yes, so now we will talk a bit about the moduli space of curves. So the moduli space of curves is just the set of Riemann surfaces of genus G with n marked points. Then you endow this with some topology and some extra structure to make it a moduli space. And well, the curves are taken up to B holomorphism. And we can build the linear-Mumford compactification. So it includes also, apart from smooth curves, so I didn't say here, but here for the open moduli space, we are taking just smooth curves, so curves that look like this. And for the compactification, we also include nodal curves, actually what we call stable curves. So yeah, there's some extra conditions. So we can build some natural bundles over the moduli space of curves. So if you take, for example, the ith mark point at every curve, this gives for you a line bundle. So, and you take the cotangent bundle, so the cotangent line at every point. This gives you a line bundle over the moduli spaces that we call Li. And since we have n marked points, we have n of these natural line bundles Li. Then if we take the first Chern class, we define what we call the psi classes, which are the main characters of these cohomological field theories that I will introduce. So they live in the second cohomology group of MGN bar, and we have to take coefficients in Q. And then, yeah, we can compute intersection numbers, or we can also call them correlators from the language coming from physics, by just integrating these psi classes to certain powers. And this will be 0 unless we have that this is equal to the dimension of MGN bar, that is 3G minus 3 plus n. And we are interested in this type of numbers because they give us a lot of interesting geometrical information about MGN bar. So, okay, let me state the Witten's conjecture. We can build the generating series of these intersection numbers. And the conjecture tells us that F satisfies the Korteweg-de Vries hierarchy. So yeah, actually here you can just see the first equation that is called the KdV equation. And the hierarchy is just an infinite family of compatible PDEs. So Witten's motivation for this conjecture, you probably know, but just in case, it's a very nice physical motivation. You take two different models of 2D quantum gravity, and they should coincide. So as usual, you have an ill-defined integral over all the metrics on your surfaces. And to make sense of this, you have two possibilities. One is you discretize the surface, and then you sum over triangulations. And then you send the number of vertices of these triangulations to infinity. And this is known to be governed by KdV. Or you can first integrate over conformal classes, and then you are left with integrating over the moduli space. And this is how Witten made his conjecture. which from a physical point of view is very natural, but this was mind-blowing for mathematicians because they were not able to compute these numbers just from algebraic geometry, and these are very important numbers in algebraic geometry. Then the conjecture uniquely determines F. So yeah, here I'm just giving an explicit version of Witten's conjecture in case you want to compute, because first I was cheating and I was not giving the whole explicit hierarchy. So you can define Virasoro operators like this. They are indexed by integer numbers from -1 to infinity. And yeah, the conjecture is equivalent to saying that Virasoro constraints annihilate the exponential of the free energy, so the partition function. And yeah, this was proved to be equivalent by Dijkgraaf, Verlinde. And Witten's conjecture was proved just 1 year later. Yes, 1 year later, because it was formulated in 90 by Consevich. So yeah, in 1990, Witten formulated his conjecture. Then Consevich in 91, he defined certain graphs that I will also call maps in this talk. He showed that they satisfy, so he showed that they are related to a matrix model. He was able to relate this matrix model to the integrable hierarchy. On the other hand, he related the graphs to intersection numbers, and like this, he gave a proof of Witten's conjecture. Nowadays, we know a lot of things about this problem. In particular, we know all the relations to topological recursion directly. So if you apply topological recursion to the so-called airy curve, is the simplest spectral curve that you can imagine. So if you take this, so if you're interested in understanding this topological recursion, I encourage you to do this computation for some lower topologies and find the right numbers. You should be finding exactly these Witten-Consevich intersection numbers. Okay. Yes, then let me give the definition of these cohomological field theories, and then we will see this example later. So we have a vector space with a non-degenerate symmetric bilinear form. A cohomological field theory is a collection of morphisms that go from the nth tensor product of the vector space to the cohomology of MGN in such a way that they satisfy some axioms. So the first axiom is that they should be invariant by the symmetric group applied to these copies of V and also to the n mark points. And also they should behave well when the surface is degenerate, as you can imagine from the name cohomological field theory. So yeah, just a little illustration. You have this gluing map. So in here you have surfaces of genus G-1 and n+2 mark points. You can glue the two last mark points, and then you have something in MGN because you have increased the genus and reduced the number of points by 2. Then we know that the class given by the cohomological field theory in here, if we pull back by Q, we should be getting the classes in here. And the last two insertions are given by this dual. So it is the dual of eta, which is the symmetric bilinear form. So, okay, you have this type of compatibility relations, as you can imagine. And in general, as we did for Witten-Concevich's case, we can define these correlators. So they are just integrals of this class with products of psi classes. Then some easy examples, because they are in dimension 1. So we just take vector space Q and this simple symmetric bilinear form. Then we have the trivial cohomological field theory, which is not that trivial because, okay, as a cohomological field theory, it just gives 1 all the time, but it gives rise to Witten-Consevich intersection numbers. And we also have this other cohomological field theory given with this exponential of this kappa 1 class, which, okay, is the push forward by the forgetful morphism of the last mark point. And this gives the correlators associated to this cohomological field theory are Weil-Peterson volumes, which are related to hyperbolic geometry, in case this tells you something. So a cohomological field theory defines all the time a quantum product on the vector space, just given by the topology 0,3. And it's commutative by the first axiom, so the symmetry that I told you, and associative by the second axiom, so these compatibility conditions. We say that it has a flat unit, So we say that it has a flat unit if there is a special element of V that is the unit, okay? I don't give the details of this, but you can probably imagine. And we say that it's semi-simple if the algebra given by V, sorry, this is a typo. Oh no, well, okay. The algebra given by V with this product is a semi-simple algebra. And then there is a group, which is called the Giventhal group, acting on semi-simple coFTs. This is very important because this allows us to classify all semi-simple cohomological field theories. And in this very nice result of Telemann from 2012. So it just tells you that there is a certain R matrix that gives you all the information of your cohomological field theory. So there is a topological part that is just the degree 0 part, and which is easy to compute. And you have also some techniques to compute the R matrix. And with this, you have all control on your semi-simple cohomological field theories. And here is one example of a more complicated cohomological field theory. First of all, the vector space is not of dimension 1 as before, but also this one is non-semi-simple, and it's Witten's R-spin class. I will not give a lot of details of the definition because it's really complicated in higher genus especially, but it's just a class that looks like this. So each element of the vector space has associated some number between 0 and R-1, and these are called the primary fields. And then this class is of pure degree, pure cohomological degree, given by this quantity. And if this quantity is not an integer, it just vanishes. So, okay, this is a more complicated cohomological field theory. Then a very interesting relation between cohomological field theories and topological recursion. So this was established already for some examples, as I explained, for example, for Witt and Kontsevich. But the very important relation came with these more general results by Enard in 2011 and Dunin-Bartkowski on Tan, Shadrin, Spitz in 2014. This is sometimes called the DOS correspondence because of the initials. This gives a correspondence between topological recursion for spectral curves with simple ramification points and semi-simple cohomological field theories. What does this mean? So this means that if we take a spectral curve with simple ramification points, so what I defined at the beginning, we can always compute a semi-simple, so the correlators of a semi-simple cohomological field theory. So we run the topological recursion and there will be a cohomological field theory appearing. And we can also do the other way around. If we have a cohomological field theory, we can build a spectral curve whose topological recursion will compute the correlators of this cohomological field theory. But this result is only valid for semi-simple coFTs because it relies a lot on Telemann's classification theorem. So we need other tools to study non-semi-simple cohomological field theories like Witten's class. And this is what we did in our work. Yeah, I actually didn't say it, but it's a joint work with Belliard, Charbonnier, and Enard. And you can find the archive in the outline of the talk, for example. Yes, so in '93, Witten generalized already his wonderful conjecture from the '90s to higher R's. So this time he took intersection numbers with Witten's class, which he kind of gave some heuristics for the existence of this class, but he didn't build it at all for higher genus. That was very complicated work by algebraic geometers afterwards. So he conjectured in 93 that this satisfies this time the RKDB hierarchy. And we know that for R equal to 2, this recovers the previous Witten-Kontsevich conjecture. This was proved by Kontsevich, as I said, but nowadays it has many proofs, also by Mirzakhani, Okunkov Pandaripande. They all give different information about the problem. But for higher R, there is only one proof, and it was in 2010 by Faber-Schadt and Zwontkin. And it's very nice that there is this proof, but it doesn't give a lot of information about the class. So there is still a lot to be understood about this class. So this motivated us to say, can we complete the picture that we had, we understand very well for R equal to 2 in the general R case. And in particular, we wanted to study the combinatorial side, because usually that's the first easiest side to attack topological recursion. In this case, it was not that easy, but okay, in the end, we managed. And yeah, here I wrote higher topological recursion because since this is non-semi-simple, we actually need higher ramification points. So I didn't even define this topological recursion, but okay, there is a procedure to do it. Okay, so let me give some details. So I will define what we put in here. So I will be saying graphs and maps from now on all the time. I mean the same thing. So they are just some graphs embedded on surfaces that they are usually called maps. Actually, a map of genus G with n boundaries is an embedding of a graph into an oriented surface X of genus G in such a way that the complement of the graph, so what we call the faces of the graph, is a disjoint union of disks. So we only allow the faces to have the topology of a disk. So it's the simplest possible case. And we consider n faces that are special, and this we call the boundaries. And yeah, there is some isomorphism relation. Okay, so for example, here a map of topology 1, 2 is just a graph embedded on a surface of genus 1. And it has these two arrows that mark two of the faces, and we call them the two boundaries. This, for example, is an example of graphs embedded on a torus and here on the sphere, but I just draw it on the plane. But they are not maps because the gray faces, they don't have the topology of a disk. So, but we can add some edges, and then they are valid maps. Just to give an example of something that is not a map. So this is the simplest type of map that exists, and they are related to topological recursion as well. But now we will define a bit more complicated one. So I will not give a lot of details here, but just to give you an idea. So we call these generalized Kontsevich graphs or ciliated maps. We have a lot of names because there are many different subsets. So I will give a bit of the characteristics of these maps increasing. So in here we have two types of faces. Some faces are marked, and they are just marked because they have special weights, this Z1, Zn. So we have n boundaries. We associate these weights to the n special faces. Those are the boundaries. Okay. And then we have a lot of internal faces that are decorated with some lambdas that go from lambda 1 to lambda big N. Then we can also add some white vertices, and the white vertices have some constraints. There is only maximum 1 per boundary. Then the next set also features some square vertices because the black vertices have these constraints that the degree is between 3 and r+1, and the square vertices don't need this constraint. Okay, this is a bit technical. And then the last set allows the white vertices to have a degree higher than 1. Here they only had degree 1. And they have to satisfy this so-called star constraint. Okay, so it's easier to say something that doesn't have the star constraint, which is this one here. So the star constraint just tells us that the phases around the white vertices have to be different. In this case, these two are the same phase, so this doesn't work. Okay, but this is a bit technical condition. So these sets of maps that I defined here for fixed topologies and fixed R and some weights already, they are infinite. But if we fix the degree, so if we fix this quantity, the number of edges minus the number of vertices, or it's also related to the number of faces, of course, by Euler formula, then fixing this degree and the topology, these sets are finite. And then we can introduce generating series. So it's always a good idea if you want to study families of objects to encode them into generating series. So yeah, I give a bit the elements for the generating series. So we consider that the potential of the model is just a polynomial that looks like this and depends on R. It has degree R+1. We also have these weights. So the weight per edge that in physics is called propagator. It looks like this. It also depends on V. The weight per black vertex looks a bit complicated, but this I will show later where this comes from. And yeah, and then the white vertices have just weight 1. So the weight of a map is constructed just by every edge we put the propagator, every black vertex we put the weight, and every square vertex we put the special weight. Okay, so the generating series is just the sum over the set of all these weights over the number of automorphisms of the graph. And we have this formal variable that takes care of the degree. So these are formal power series in the parameter alpha to the -1. And then they are polynomial in the other parameters. And then we do analogously for every set that we defined. And let me give a little example. So for topology 1,1, and the lambdas equal to infinity. So this means that we don't have internal phases. So this is an easy case. We can compute the degree is just R+1 because n is equal to 1, g is equal to 1. And then we can see that it only has 4 graphs because there is only one phase. So if you see the possibilities, these are the only 4 possibilities. And you can build the generating series. For example, just to give you a little idea, here you have 5 propagators. And since you only have one phase, it's very easy because you put the same weight everywhere. So you have 1, 2, 3, 4, 5 propagators. Here you put the 5 propagators, and you have 3 vertices, 3 valent vertices, and this you put here. And you do the same here. You here instead have a vertex of degree 5 and 3 propagators, and then here you actually have the same weight. That's why you have a 2. Then you can compute this using some properties, some nice properties of these weights. I don't give the details. Here I just want you to remember that all these sets that I defined are related to each other using combinatorics in a nice way. So this F that I defined is related to W, W is related to S, and everything is related to U. This is all technical things that we need for our proof. So just a very fast sketch of how to prove topological recursion for these graphs. So the idea is to find this touch recursion. So what we do is we erase the first cilium. So the cilium is just the edge that goes to the white vertex. And we introduce a bivalent white vertex on the following edge around the square vertex in the clockwise direction. So for example, we have 4 different cases for this. One is when the following edge is adjacent to a face decorated with lambda j. So here we erase this. We introduce this bivalent vertex. This equality is very easy because we are just compensating the propagators that we need to compensate because we just changed a bit the graph. Then this equality is more difficult. It follows from the previous technical equalities. And the contribution coming from all these graphs that are kind of simpler than this graph is computed by this generating series. Then we do the same for 4 different cases. The case in which the following edge is adjacent to a decorated face, then we need to use a relation, and it's very, then it gets very similar to the previous case. The contribution looks very ugly, but we don't care. We can, you can believe me that we can compute it. Then the case in which the adjacent phase is the same in here. In this case, it's very nice because it factorizes and it gives this typical term from topological recursion that factorizes the topology. And then the last one is also gives this typical term from topological recursion, g minus 1 and plus 1. Maybe it rings a bell. It's this case. It's the same case, but in here you have something connected. Okay, so from here we got a recursion on 2g plus n plus d. So also on the degree. So these guys all have smaller quantity like this than these guys. So it's a kind of recursion. You can use it to compute, but it's quite complicated. So what we want to do is to just find a recursion on G and N. And this will be the topological recursion. And okay, this is very, very technical. Yes.
Can I just remind you that you have like 5 minutes left, more or less. Okay.
Thank you. So yeah, I will just wrap up a bit the ideas for you to see how this works. But of course, it's impossible to see all these details. So yeah, we get the spectral curve from the base topologies. So yeah, maybe let me just go to the sketch of the proof. We just got the recursion that is called alatat. We get the form of the spectral curve from topologies 0, 1, and 0, 2. So topology 0, 1, and 0, 2, usually you can compute because it's genus 0. You have little insertion, so you compute explicitly. This is how you get the spectral curve. Then this is very technical, and I was never intending to talk about this, but in case someone wants to know the details in later, and maybe it's useful to have it. So we gave combinatorial interpretations of certain universal expressions that have to do with loop equations, if you know about loop equations in other contexts. So we find the analytic properties, so the polar structures of our generating series. These combinatorial interpretation of these universal expressions, they imply these loop equations. And then these spectral curve, these loop equations, and these analytic properties, they give us topological recursion. So we just take the complicated recursion that we had, and we do some, we use some clever techniques coming from topological recursion, using complex geometry to reduce it to this easier formula and more universal formula. Then we actually do this for classical topological recursion, so simple ramifications, but to make the connection with the intersection numbers that we want, we need to collapse some of these ramification points to a higher ramification points. Okay, this is what I'm saying here. And just to give the idea of what we do, we just define these generalized maps. We proved they satisfy topological recursion. We also proved that they are related to the matrix model, generalized matrix, Kontsevich matrix model. They that this satisfies the RKDV hierarchy. And then we use this arrow to establish the relation between the intersection numbers and the graphs. And with this, we establish that the intersection numbers also satisfy topological recursion. So this is the sketch of the ideas. And then in the next slides, you can have, okay, maybe this I will give a little motivation because this is how we defined our graphs. So this is a usual Kontsevich matrix model. You have just trivalent vertices in the usual case. And there is a natural generalization. So to just put here any potential like this. So kind of now 3 goes to R plus 1. And using some tricks to be able to use this Weeks theorem to compute the Feynman graphs, you can make this partition function into this shape. And here you can see the propagators appearing and the weights for our black vertices appearing. So this is how we defined our graphs. So it was, the motivation was coming from generalized Kontsevich matrix model. Then, okay, We can also relate the correlators to our ciliated maps. And yeah, some other correlators are related to the topological recursion with extends X and Y, which is a very important transformation in topological recursion. Yeah, here I gave some details on the Wittens class, but let's skip this. And finally, yes, I can just comment a bit what I explained in the diagram. We are able to go directly from the graphs to the intersection numbers using just that the partition function of the matrix model is related to RKDV. And then we use Faber-Châtillon-Zonkin to relate intersection numbers to RKDV. And then we use 1, 2, and the relation to the graphs via the matrix model to relate the combinatorial problem to the intersection numbers. And these type of formulas that relate these things, okay, this in particular looks very, very ugly, but these type of formulas are called ELSV-like formulas because they allow to translate things from combinatorics to intersection theory. And yeah, it's nice because sometimes you can compute nice things in combinatorics and bring them to the other side or the other way around. And this is what I did here to complete the example of before. I just took what I had shown you before. I specified to this particular potential that is the one that gives us the intersection numbers. Then we use here the ELSV formula. So here we are using the relation between what we computed from graphs and the intersection number. And this allows us to recover this intersection number that is otherwise very difficult to compute from algebraic geometry. Yeah, and then so far, this is the paper with Béliard, Charbonnier, and Now that I told you about. This also has some consequences in combinatorics that we can discuss later if someone is interested. There is also some work in progress to understand better the algebraic geometry of this class from topological recursion and some wilder ideas that also come from this work. Yeah, thank you for your attention.
Thank you very much, Elba, for this very, very nice talk. Yeah, so please, questions. Yeah, we already have 2. So, Jan.
Thank you very much. Yeah, those are interesting. So somewhere in the middle, you said that you get an associative product from this omega 310.
Yes.
So this means that there is no differential somehow, right?
That there is no differential?
No, there is no omega 20 maybe. Or a differential. Is that correct?
Yes, yes, yes. Because what happens for 0,2 is that it's an unstable topology. So it's kind of trivial because you only have genus 0 and 2 mark points. And then that is not considered, that doesn't define a good moduli space. So it's discarded. So it's kind of trivial.
Okay. In the operatic theory, this is included in a different way. Okay.
Okay. I don't know so much about the operatic language, but I would really like to know more.
Yeah, we can. Yeah, maybe we can talk about it. And then you had this overview of this cohomological field theory. There was this there were these maps from somewhere to that, or from vector space power n to somewhere.
Yeah.
So can you tell, like in the example you presented or in the result you presented in the second half? So what was the vector space and what was the other side in this case?
Yes. This I did very fast. Or maybe it's even better to go here to the slide that I skipped. Yes, here the vector space is just some R minus 1 dimensional Q vector space. And the two non-degenerate form is just delta like this, that is A plus B has to be equal to R minus 2. And yeah, and then these vectors are labeled by these so-called primary fields that are just numbers from 0 to R minus 1. And you define your Witten's class on these vector fields by just this class that is a bit complicated to define, but okay. But this is the vector space. It's just it's pretty easy, but okay. The fact that it's higher dimension than one already makes it much more difficult.
Okay. Maybe and last thing, this R, it is what?
Sorry?
The R, the index R. What is it?
It's just an integer bigger or equal than 2.
Okay. Does it have some kind of physical interpretation? If it has some kind of physical interpretation, sorry.
Yes, yes. I don't know. Maybe someone someone has a better view on this. So in the classical Witten conservative result, R is equal to 2. And for me, I think more of the geometrical interpretation. This just tells us that the Strevel differentials of the moduli space that we need to consider will be trivalent. So they will only have trivalent vertices.
Okay. Thank you.
Yes.
Thank you very much.
You're welcome.
So there's one more question. Nima, please.
Yeah, thank you very much for the great talk. So my question is more on something conceptual. So I was reading recently about this whole topological recursion story, and I was wondering, do you know how, like, or is there some reference of how you can combine this into like Kodaira-Spencer gravity in the guise of, I would say, like Costello and Lee?
I don't know. I don't know.
I mean,
I can.
yeah,
it seems
seems somehow natural, because there you can build actually a BV theory where you describe like the action somehow in terms of its power series, of its Taylor expansion, where the in the Taylor coefficients somehow are given through Gromov-Witten invariants, but then you just use like the moduli of stable maps, but whatever. And I mean, right? I mean, you have a lot of I mean, the whole story is about Gromov-Witten somehow. So I guess there should be something, right?
Yes, probably.
I think this would be very interesting, right?
So you would like a direct relation to what exactly?
So the relation would be to Kodaira-Spencer gravity or BCOV theory, you know?
Okay. Do you have some correlators labeled by maybe G and N there?
Yes, of course. That's what I'm saying. It's like you have the theory of which was built by Costello and Lee, okay. I think in 2012 or something, where they do this like for like Calabi-Yau, like general Calabi-Yau basically, and then you can the action function that they have, what they actually do is they formulate a BV theory. So this would also relate your construction to Badal and Minkowski, and so they describe the action in this Kodaira-Spencer gravity basically as in terms of its Taylor expansion, and then you can the coefficients, like basically the action is given in that sense in terms of Gromov-Witten, right, on this invariants, right, which are modeled over the moduli space of stable maps, right? And so you have this there, right? So
yeah, it really looks like there should be a connection. I don't know if it would be difficult to prove. It could be that it would be difficult because proving Gromov-Witten, I mean, it could be that it's included in some of the general theorems already, but if not, it's probably.
I mean, it's not about the higher classes for this higher R. It's just the usual thing. It's just the usual intersection number that you have. Okay. I mean, I don't know. I think it would be interesting just to relate these stories somehow.
Yeah, sure. So I don't know, for example, of any direct relation to BV formalism. So
yes, maybe we can talk afterwards in the discussion session. Yeah. Thank you very much again.
You're welcome. Thanks for your question.
Let us thank Elba again. And yeah, I would also suggest that further, that we continue the discussion later on, and now take like a 4 minutes break and come back at 11.
Okay.
Okay.
Mhm.